Well, now we have a paragraph based on which next 3 questions have been asked. The paragraph says, in the arrangement shown, the separation between slits S3 and S4 is variable, denoted by Z. Intensity due to each slit S1 and S2 is I0. OO dash is central line. This is the central line. And question 6 says, if Z is equal to this much, then intensity at point O is. Okay. So if Z is this much, we can take that this distance is Z by 2. And if this distance is Z by 2, then the value of Z by 2 is equal to 2 times lambda capital D by small d, right? Now we consider interference at S3 and S4 due to these 2 slits, right? Now if we do that, this is the value of y, okay, and we know that the path difference for the waves coming from S1 and S2 at S3 is given by the expression d times Z by 2 by capital D, dy by d small y by capital D, here small y is Z by 2, and this is then equal to d by capital D, and Z by 2 is 2 lambda capital D by small d. We can see that this value is coming out to be 2 lambda. So that means there is going to be constructive interference for the waves coming from the 2 sources at S3, and same thing is going to happen at S4 also. So that means if we consider that intensity due to each slit is I0, then here intensity will become 4I0 because of the constructive interference, right? The amplitude will be twice and the intensity is proportional to square of amplitude. So here we are going to get intensity as 4I0 and 4I0. So due to both the sources. Now if we consider that on this screen intensity due to each screen is 4I0, then at point O obviously the path difference is 0 and there is going to be constructive interference at O also. So here the intensity will be 4 times intensity due to each of these screens S3 and S4 because of the constructive interference, right? The logic that we applied, the argument, the concepts that we applied for points S3 and S4. Similarly, here due to constructive interference, the intensity here is going to be 4 times intensity due to each source, right, on the screen. And if we apply that, then intensity at O will be 16I0. If here it is 4I0, then here it is 16I0, which means for question 6, option B is correct and other options are incorrect. Let's go on to the next question now. Now question 7 says, if the value of Z is this much, then intensity at point O is. So first of all, we find intensity at screens S3 and S4, and for that we find the path difference. Well, the path difference will be then small d by capital D into Z by 2, and the Z by 2 is lambda capital D by 6d. This is the path difference, and this is equal to lambda by 6. The phase difference is 2 pi by lambda into path difference, that means into lambda by 6. We can call it phi, and this is equal to pi by 3. Okay, so if the phase difference is pi by 3, then intensity at S3 can be written as I0 plus I0, intensity due to each of the slits, plus 2 times under root I0 into I0, which is going to give us I0, into cos pi by 3, which is 1 by 2. So this is coming out to be 3I0. So if intensity here is 3I0 and 3I0 here, due to constructive interference at O, it will become 4 times of that, and so the value of intensity at point O, by extending the arguments of the previous question will be 12I0. So for question 7, the correct option is B. Let's go to the next question now. Question 8 says the minimum value of jet for which the intensity at O is 0 is. Okay. Well, for intensity at O to be 0, intensity at S3 must be 0. So that means we have d small d by capital D into z by 2. This should be odd multiples of lambda by 2. Now since we are talking about minimum value of z, then that odd multiple of lambda by 2 is simply lambda by 2, and if we solve, then value of z comes out to be equal to capital D lambda by small d, and which is matching with option A for question 8. So option A would be taken as correct for question 8. Let's go to the next question now. Well, we now have the paragraph for the next 3 questions, and it says in the series LCR circuit shown in the figure, the inductor coil has resistance 36 ohm. That is given, and we have this AC circuit. And question 9 says the potential difference across the coil is nearly. So now the coil has inductance of 90. In fact, coil has inductive reactance XL of 90 ohm, and it also has resistance R2 equal to 36 ohm, whereas the capacitive reactance X is 30 ohm, and there is another resistor of 44 ohm connected in series. It's a series LCR AC circuit. Okay, so to find potential difference across the coil, let's first of all find the impedance of the circuit. Okay, now to find impedance, first of all you find that the total resistance is 44 ohm plus 36 ohm, and that is equal to, let's say, R1 plus R2, and this value is 44 plus 36, that means 80 ohm. Now XL is 90 ohm and XA is 30 ohm, so XL minus XC we can write as 90 minus 30 or simply 60 ohm. So the impedance Z is going to be equal to under root of R square plus XL minus XC whole square, and that means is under root 80 square plus 60 square, and that value is 100 ohm. So this is the impedance of the circuit. So that means the current in the circuit, the RMS current will be 200 by 100 or simply 2 ampere. Okay, now to find potential difference across the coil, let us draw a phasor diagram for the current and voltages, right? Because there are 2 types of potential drop across the coil, one across the resistance and one across the inductance. So suppose this is the phasor for current I, then if I call potential difference across resistance R2 as VR, then VR will be in phase with current I, and so let's say this is VR, and its value is 36 into 2, that means 72 volt. Okay, I into R2, and that is 72 volt. Whereas the potential drop across the inductor will be VL, and VL will be leading in phase the current by pi by 2. So VL we can draw like this, and its RMS value is equal to XL into I. So XL is 90 ohm, 90 into 2 is 180 volt, and we have to superpose, in fact we have to find the resulting phasor of the voltage. We can apply the Pythagoras theorem, and this will be the potential difference. This phasor is going to give us the potential difference across the coil. So this was 180 volt and 72 volts, so we have under root of 180 square plus 72 square, and if we simplify and solve, this value is close to 194 volt. So the potential difference across the coil is nearly 194 volt. So option D is correct. Let's go to the next question now. Question 10 says power dissipated in the inductor coil is, and the 4 options are given. Well, we have already found the current, the RMS current, which is 2 ampere, and the power essentially will be consumed due to the resistance of the coil. We know that due to the inductance, the power dissipated in a cycle becomes 0, right? So that means the power dissipated in the inductor coil, it's nothing but P, let's say it's PC, it is equal to I RMS square or I square into R2, and that value is 4 into 36, which is coming out to be 144 watt, and which is matching with option C. So option C is correct. Let's go to the next question now. And the question 11 is about power delivered by the source. Well, the power delivered by the source is essentially being consumed by the resistance in the coil as well as the other resistance R1. So power delivered by the source will be then, power by source is simply I square into R1 plus R2, and which is I we found is 2, so it's 4, and R1 plus R2 is 80 ohm, so this is 320 watt. And if you look at the options, it is matching with option A. So option A is correct for question 11. Let's go to the next question now.